So now we're going to talk about a different way of solving circuits. Series and parallel is all well and good, as long as you only have one battery. But when things get more complicated, Kirchhoff's rules always work. So to show an example of a place where series and parallel wouldn't work, I have a circuit with a 5-volt battery and a 1 ohm resistor, and then a 12-volt battery and a 2 ohm resistor, and then a 3 ohm resistor. So you would guess that this battery is going to make current flow out this way, but this one's going to make it out this way. So they're maybe fighting against each other, or maybe they both go around this way. Not really sure. But if this is making current flow this way and this is making current flow this way, they would combine to make current flow here. So we would have 3 different currents in this circuit. So if I use colored pencil to label this, there's going to be one current coming out of this battery. But because this is one branch, we call it, there's one line, everything's just connected with wires, all of this is I1, okay, going around this branch of the circuit. Well, the middle one makes a current away from the positive. Well, and that same amount is going into it on the other side. So this is I2. And then our supposition right now is that these 2 currents, then since they're both making current flow here, there's going to be a 3rd current that comes around this way. And these are 3 different values of currents. And you can't use series and parallel to find these. But the first thing we can do is apply what is called Kirchhoff's junction rule. So a junction is a place where any 3 or more wires meet. So this is a junction, because we have 3 wires there. This is a junction. This is not a junction, this is just a bend. But this is a junction where current has a choice. So a good example would be right here. I3 gets here and it chooses, some current goes this way, some current goes this way. So on a parallel circuit, right before and right after the parallel combination are junctions. So Kirchhoff's junction rule says all the current that comes into a junction has to flow out of the junction. And that makes sense. Current flows in, current flows back out. Just like if this is water in pipes. Water in, all the water has to go out. Now really, this is a statement equivalent to conservation of charge. Remember, this is all electrons. Now electrons are going the opposite direction, but if we just go with it, these electrons, when they get to a junction, do not magically disappear from the circuit. Extra electrons are not added to the circuit. Electrons are just energy delivery trucks. They keep going around the circuit, pick up some energy here, deliver it to this resistor, deliver it to this resistor. Pick up some energy here, deliver it to this resistor, deliver it to this resistor. Pick up some energy here, deliver it to this resistor, pick up some more energy, keep going. All sorts of different paths for these electrons to follow this time. But the electrons don't disappear, and more of them don't reappear, magically appear, whatever. So current in equals current out at every junction. So for this diagram, at the top we have current 1 coming in plus current 2 coming in. Both of them are flowing into that junction, but I3 is flowing out. Now we can do the same thing at the bottom junction. Into the bottom junction is I3. Out of the bottom junction is I1 and I2. So these rules, or these equations are the same. This gives us one piece of information, but it doesn't give us enough to know what I1, I2, and I3 are separately. Now, if I told you 2 of these, hint, hint, that's the first problem, or the second problem you're going to do. If I tell you 2 of these, you can figure out the 3rd one using the junction rule. But if you have a totally unknown circuit like this, where you don't know any of the 3, this is only one piece of information, because these are the same thing. So we're going to have a second rule. By the way, who is Kirchhoff? I have no idea. It's a German-sounding name, and he did some important stuff to get these rules named after him. So we also have Kirchhoff's loop rule. And in words, his loop rule is that the sum of all delta V's, potential differences, around a loop, so a closed path, so you start one place, you end up at the same place, equals 0. This is equivalent to the law of conservation of energy. Because remember, potential is potential energy per unit charge. So when these electrons are going around the loop, they pick up energy, they give away energy. They pick up energy, they give away energy. They pick up energy, they give away energy. So the amount they pick up, they have to give away so they can pick up more. They have to lose all their energy before they go back inside the battery. So sum of all potentials around a loop equals 0. So we need to do some sign conventions. We are going to travel around the loop sometimes with the current and sometimes against the current. Like let's say if we do this left loop here. On this side be going with the current, but on this side my finger is traveling against the current. So if we have a battery with EMF E and we are traveling this direction, you know what? Let me change that to red. Our direction of traveling is going to be red. If we are traveling to the right, this positive charge, again, we hate Benjamin Franklin, this positive charge as it passes through the battery is gaining energy. This is what batteries usually do. So the potential difference across this is equal to positive EMF. But if I have a battery this way in the circuit, and I'm traveling this way, so that would be in this circumstance when I get to this battery. I'm going backwards across the battery. I'm going from the positive side to the negative side. My travel is opposite what we think of batteries as doing. So the potential for this one is negative EMF. Okay? So if you go the way you think batteries usually work, or the battery, almost always they do work this way. If you go across the battery this way, then it's a positive value of EMF. If you go across backwards, like you're going against current flow, then it's negative EMF. And we have something similar with resistors. If we have a resistor, resistance R, and the current is flowing to the right, and we travel to the right, so that's again in this part, we are traveling with the current here across this resistor. Well, we know current, the charges are dropping off energy in this resistor to be converted into heat or light or motor or whatever electronic device this is. So if we go across this, the circuit is giving energy into another form. So the potential difference is decreasing. There's less energy in the circuit because it's going out of the circuit, it's going into a different form. And we know potential difference, V, is I times R. So this is I times R. And then last possibility, if we have a resistor and current is flowing that way, but we're still traveling to the right. So we are traveling opposite the current. This is like swimming upstream against a water current. That takes a lot of energy because you're gaining energy, you're going upstream. So we're not giving electrical energy to another device, we're bringing it in if we're going the opposite direction. So delta V in this case is positive I times R. So I want to apply these to a couple of the loops in the original circuit. So how can I get all of this on the screen at once? Well, right here. I'm going to do the left loop. So for the left loop, get one more color. I have to do a whole loop. I have to start and end at the same location. So I'm going to start right here. Does that show up? Yes. And I'm going to go clockwise just around the left loop. So I'm going to go this way, and then this way, and then this way, and then back to here. So when I do that, I'm going to go through this resistor, or across this resistor, through this battery, and across this resistor. So I'm going to get all four things in one. So I start here, and it's bare wire. So there is no potential difference across a bare wire. If I had a number, like if I knew the actual potential at this point was 0, then before I get to the resistor, everywhere along here is still 0. But then I get to this battery. Excuse me, resistor, shame. I'm going to cross this resistor. When I cross this resistor, I'm going with the current. This red current is pointing towards the top of the page, and I'm traveling towards the top of the page. So since I'm going with the current across the resistor, the potential difference is minus I times R. So that gives me minus I1, which I don't know, times R, which is 1 ohm. Okay? Then I keep going, bare wire, so nothing changes. So whatever this value is, the potential is still the same. And then I get to this battery, and I'm going to go from the short to the long side. So I'm going from the low potential to the high potential side of the battery. I'm traveling in the normal direction we think of as a battery, so I'm going to gain potential. So I'm going to gain 5 volts. And I'm leaving units out since I have I for variable, and it's confusing. Then, as I continue around my yellow thing, my nice pretty yellow loop, bare wire, bare wire, bare wire, no potential difference, no potential, and then I turn and I'm going down through this to get back to my first point. So now I'm going to travel across this battery from the high side to the low side. I'm going to lose 12 volts across this, because if you go backwards across a battery, you lose potential. And then keep going to this resistor. Well, I'm going across this resistor from the top to the bottom of the page, continuing my yellow loop. Because I'm going down, I'm going against the current. When I go against the current across the resistor, I gain potential. It's like swimming upstream. So I need to do plus I times R, I2 times 2. And then back across bare wires, no potential difference, and I'm back to where I started. And I have 0. So, you may have been wondering, why would we ever do such a thing, besides just to show how Kirchhoff's loop rule works? Well, just about all electrical devices that you run into are much more complicated than plain series and parallel. And so electrical engineers don't do series and parallel. They use the junction rule and the loop rule to solve whatever information they need to calculate about a particular circuit. Like maybe they need a particular current output or a voltage output, or in the middle of it there's a device that if you have too much current through, it's going to blow. So they have to limit that. So if this was a circuit they were analyzing, they need to know, so what are the values of I1, I2, and I3? What are these numbers? Well, we have a slight problem. We've got one equation, because remember this is a duplicate, but we've got 3 variables. Well, now we have a second equation, and we could simplify this a little bit. In fact, if we do, we have negative I1 minus 7 plus 2I2 equals 0. And I could make that prettier. 2I2 minus I1 equals 7. But I still have a problem. I have 3 unknowns, and I only have 2 equations. So I need to do the loop rule again. So I'm going to do it one more time, and unfortunately it's not all quite going to fit on the screen at the same time, so I'll just have to move the book up and down, and life goes on. So we could do the right loop or the outer loop. I'm going to do the outer loop. Outer loop. Now, one of the advantages of doing the outer loop, if I can find a different color highlighter, I'm going to start at the same place. I'm going to go the same direction. And by doing that, the first part of my equation is the same because it's my first part of my same loop. So I'm going to go with the current across this resistor, so I'm going to lose I times R, so minus I1 times 1. I'm going to gain across the battery because I'm going the normal direction, so I'm going to gain 5 volts. So let me slide this down. I'm going to copy this first part. Minus I1 times 1 plus 5. Then, after the 5, bare wire, bare wire, bare wire, bare wire, bare wire, bare wire, that's starting to sound weird, and I get to this resistor. Now I'm going down as I trace my loop. My current is down, so I'm going with the current. So when I do I times R, 3 times I3, with the current is a negative sign because I lose potential. I lose energy from the circuit converted into a different form. So minus I3 times 3 equals 0. Sorry, that wasn't quite on the screen. So again, I can simplify this equation. I get minus I1 minus 3I3 equals negative 5. Well, let's multiply that whole thing by negative 1. So I1 plus 3I3 equals positive 5. So I'm going to turn the page and copy the first equation we got from the junction rule. I1 plus I2 equals I3. And then from the left loop, we got 2I2 minus I1 equals 7. And from the outer loop, we got I1 plus 3I3 equals 5. So at this point, I should tell you, solve these 3 equations. It's really not that hard to do 3 equations and 3 unknowns. My personal suggestion to you would be pick one of the 3 to get rid of. Like maybe you're going to choose to get rid of I3. So if you substitute this equation into this equation, then this would only have I1 and I2. And then you could solve this one for I1, plug it in here, and then you'd only have I2, and you could get the answer. So I'm going to skip ahead and tell you the answers. The other way you could do this, by the way, for those of you who remember how to do it in your graphing calculators, is to turn this into a matrix. This is a whole branch of math called linear algebra. There are no squares and square roots and inverses in this equation. All of these directly depend just on I1 or I2 or I3. So they're all linear equations, and you could use matrices, linear algebra, to solve these. But we're not going to do that because the College Board will actually never give you something this many that you have to solve. Their limit is 2, and you'll see one of those on the assignment in class. So when you solve, you get 3 numbers. I1 is negative 1 amp, I2 equals 3 amps, and I3 equals 2 amps. So I'm going to flip back to the picture. I1, this red one, was negative 1 amps. I2 in green, any chance I can find that green pen real quickly? Nope, it's gone. I'll just use this. I2 is 3 amps. And I3 is 2 amps. College, everything's missing. So you may be concerned about this negative sign. Here's the lovely thing about this. We didn't really know which direction current was traveling in any of these. Like we guessed that current was going to come out of the positive side of the batteries for both of them. But this battery, it turns out, is so much stronger than this that it overwhelmed this current. Current does not flow up through this side of the circuit. It flows down. So the value of this current is 1 amp, but the direction I drew in the picture is incorrect. The direction should be the opposite direction. That's another thing that's really powerful about Kirchhoff's rules is when they design a circuit, they may not know which direction current is flowing. It doesn't matter. They can guess, and they can guess all of them wrong. If they guess all of them wrong, they'll all turn out negative. Oh, okay, they're the right answers, but the opposite directions. So you're going to have some problems where you're going to apply the junction rule. There's a really simple junction rule one. You will be doing the loop rule, some. I'm going to give you some pieces of the loop where you'll start with something at 0 and then do a couple of these to tell me what is the potential at one end or at different points in a circuit. And then I'll tell you now, I'm going to give you one of these circuits. But in the circuit that I give you to solve, I'm going to tell you one of the currents. So you won't have 3 unknown currents, you'll just have 2 unknown currents because that's what the College Board will limit itself to. So if, for instance, this was the exact circuit I was going to have you solve, in these equations, if I told you I3 equals 2 amps, then you could really quickly see from this equation I1 plus 3 times 2 equals 5, so I1 equals negative 1 amps. You've already solved it, okay? So if you only have 2 unknowns, it's much easier to do than having to solve a system of 3 equations. But there's a really fun circuit on the assignment that has 6 different currents. Now, I've already solved them for you, but 6 different currents. So, Kirchhoff's rules, the last topic in current electricity just with resistors. And then we'll move on in the next unit to putting resistors and capacitors in the same circuit. And then Kirchhoff's rules are required.